In the last video, we completed the proof that in a connected planar simple graph, so no loops or multiple edges, with order 3 or more, at least 3 vertices, the number of edges is less than or equal to 3 times the number of vertices minus 6. What I want to do is use that to show that K5 is non-planar without doing any heroic manipulation of the edges, but rather just counting the number of edges and vertices to show it's non-planar. So in K5, we can actually count the number of edges. I'm going to do this above, right? So the example is K5 is non-planar. And so in K5, the number of vertices is 5. And the number of edges, because it's a complete graph, is equal to 5 choose 2, which is 10. Okay? So let's compute 3v minus 6. But 3v, 3 times the number of things in v, the number of vertices minus 6, is 3 times 5 minus 6, and that's 9. That tells us then the number of edges, which is 10, is greater than 9, which is 3v minus 6, 3 times the number of vertices minus 6. So K5 cannot be planar, because if it were, the inequality that we got right here would be the reverse direction. So that proves K5 is not planar. Let me write that a little clearer. K5 is not planar. Now, another similar inequality that we got in corollary 3 can be gotten in the special case that we know one more thing, that is that the graph has no 3 cycles. Because if it has no 3 cycles, then every region must have degree at least 4. It must have to have a walk of at least 4 edges to form a closed walk, forming the boundary of a region. The only way you could have an unbounded region of degree 3 would be if you had 3 edges in the unbounded region and all the other part of the graph took place down here, but that's a 3 cycle. So every region, including the unbounded one, would have to have degree 4. So in the same way we proved the earlier result, corollary 3, what we would have this time would be the inequality. The inequality would be that 2 times the number of edges is equal to the sum of the degrees of the regions over all regions, R in capital R, would be greater than or equal to 4 now for each of those, summed over however many there are, which is equal to 4 times the number of regions. So in the previous theorem, corollary 3, we had a 3 there, and this time we have a 4. So what that gives us is that R, the number of regions, is less than or equal to 2 divided by 4, or 1/2, the number of edges. And with Euler's formula, just as we did before, that would say the number of edges is equal to the number of vertices plus the number of regions minus 2. And R is less than or equal to 1/2 the number of edges. So this is less than or equal to V plus, right here I'll put a 1/2 times the number of edges minus 2. Subtracting this term from both sides gives us a 1/2 the number of edges is less than or equal to the number of vertices minus 2, but multiplying by 2 now would give us exactly this relationship right here. That's exactly what we need to show that K33 is not planar. The previous result wouldn't work, but in the case of K33, it does fit the requirements of corollary 4, because in K33, let me just talk about it down here, any cycle would have to go from the upper set, V1, that's a capital there, down to the lower set, V2. I'm not saying it's directly down, but someplace down. Maybe I'll show you it that way. It has to go to some vertex in the other set, say that one there. And if it's going to be a closed walk, it can't come directly back because there's not a multiple edge there, so it has to go to some other vertex up here. And then I'm still trying to get back to the start to get a closed walk. It'd have to come back down again and then back up. So the smallest cycle is a C4, a 4 cycle. So that means that corollary 4 does apply in the case of K33. So K33 has no 3 cycles. But let's count the number of edges and vertices there. It is also connected. It's connected. And it is simple. So everything else is known here, except whether or not it's planar. And so let's check and see if it satisfies the condition it must to be planar. So in K33, the number of vertices is 6. The number of edges is 3 times 3. I haven't drawn all of K3 here, right? Just part of it. 3 times 3 equals 9. And if I look at the computation that we have over up here on the right-hand side, 2 times the number of vertices minus 4 is equal to 2 times 6 minus 4, which is 8. So E, the number of edges, is not less than or equal to that. In fact, we have the number of edges, which is equal to 9, is greater than 8, and that's equal to 2 times the number of vertices minus 4. So again, we get an inequality in the direction that violates what it would have to be if the graph is planar. If the graph were to be planar, we would have to have that inequality. So this says, therefore, K33 is non-planar. And K33 and K5 are really sort of the basic non-planar graphs, as we'll see a little bit later. So before we dive into that, we now have in this video demonstrated that K5 is non-planar. Right, we have that one up here. K5 is non-planar, and K33 is non-planar. Both of those are just dependent upon calculations because they satisfy everything else: connected, simple, order 3 or more, or in the case of K33, connected, simple, order 3 or more, and no 3 cycles. So it was just a matter of showing that the counts don't work out right for them to be planar. They cannot be planar because they don't satisfy the conclusion of those corollaries. Those are the kind of proofs that I occasionally will ask on an exam. So be aware of that. So as we talk a little bit more about the basic planar ideas, and what I said that K5 and K33 are the basic planar graphs, I want to talk about what it means for 2 graphs to be homeomorphic. Let me read it first of all. 2 graphs are homeomorphic, this term here, if they have a common ancestor graph G, from which each of them can be obtained through a series of steps where we split an edge into 2 by adding a vertex within the edge. No other variations are allowed. So just a real quick example here to show you what I mean by that. So let's take 2 graphs that are homeomorphic. We'll start with a pretty simple graph here. Maybe we'll start with the graph that looks like this, and come up with some graphs that are homeomorphic. So this will be the common ancestor, and I'm going to create homeomorphic versions of it, 2 different ones, by adding vertex to split an edge and no other operation. So over here I'll redraw this graph. Looks basically like that, and over here I'll draw it. And in each case I'm going to do different things to create a homeomorphic version. So in this one here, I think what I'll do is I'll split this edge here, split that edge right there, and maybe I'll, yeah, that'll be enough, okay? And on this one over here, I'm going to split this edge 2 times, and split this edge 1 time, like so. And so I could redraw these so they don't look the same, and that's the idea, that I want to have them so they don't look the same. If I redraw this one right here, what I come up with is this graph, like so. You might wonder where the green ones went. The green ones basically, this is 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that's the outer part here is the green one. And I think I need one more vertex there to do that. So let's just put one there. And the inner one, triangle, is this triangle here that I pushed up into it. So this one right here, I have a situation now where I have 1, 2, 3, 4, 5, 6. So I have a hexagon that I could draw from that 6 cycle there. And inside of that hexagon, there is a 1, 2, 3, 4, 5 cycle. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. That's the hexagon. And then along in that hexagon, I have this 1, 2, 3. This 1, 2, 3 cycle. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Sorry, 5 cycle. So I'm going to have something of this nature here. Okay. Right. So that 1, 2, 3, 4, 5. 1, 2, 3. Yeah. That doesn't look quite right. Leave it as it is. I'll tell you what I'm going to do. I'm going to push this thing up here and push that thing inside. So we'll have this part down here. That's 1, 2, 3. 1, 2, 3. 1, 2, 3. This is the green one there. And then I'll push the triangle in there. So we have this right here. Just do that. And then the other part is 1, 2, 3. 1, 2, 3. Okay, so that's how it would look. Okay, that's a little better. There is a 5 cycle, okay, but there was no 3 cycle there, so I knew something was fishy. Okay, so those don't look very similar, well, because they're not isomorphic, but they are homeomorphic. Both haven't been got from that same graph there. So let me go ahead and pause here, and then we'll come back to do the last bit here.